Welcome to video 66 in our series on tensor calculus. In this video, we want to introduce two brand new tensor calculus objects known as projection operators. In the last video, we explored transformations to and from the tangent space, and in the process we ran across these two expressions right here. Now this one, we have the vector components of our normal projection of our vector v as a function of the magnitude of that projection over here. And on this side we have p as a function of the actual vector components of our vector v. Well, today we want to use these expressions a little differently. I want to combine them and eliminate the value of p between these two by substituting this expression for p. So it's going to look like this. We're going to have pi is equal to ni times p, but p in this form. And of course I'm using I as a free index, so I've got to use a different letter for this dummy index here. So we'll just use j, nj times vj. Okay, now this expression suggests the definition for a brand new tensor calculus object that we call the normal projection operator. Okay, and with this definition, we can now rewrite our expression this way. Pi is going to be equal to our new operator, Pij, contracted with Vj over here. So what do we have? Well, we've got an operator here that operates on our vector components Vj, and the output of this operation will be the vector components of our normal projection. So this provides us with a very simple and easy way to derive the components of this normal projection right here directly from the vector components of the vector that is forming the projection. Okay, so what exactly is this operator up here? Well, first of all, it's a tensor because we have a product of two vector components here, so that tensor product forms a tensor, and it's a tensor involving two indexes, so that makes it a second-rank tensor. The indexes are I and j, which are ambient indexes, which means they can have a value of 1, 2, or 3. So if we were going to use a matrix to represent this tensor, it would be a square matrix. It's got 3 rows and 3 columns. All right, one other thing I want to point out about it. Let's suppose, imagine if you will, that we lower the I index and raise the j index. And of course, we'd do the same thing over here. So this would form the object pji with j in the upper position, I in the lower position. Well, then if we just flip the order of these terms right here, of course, multiplication is commutative, so if we flip those, we wind up with the same expression we have here. And what that means is that the second-rank tensor is symmetric. We can flip the values of I and j and get the same expression. So it's a symmetric 3 by 3 square matrix. And as I say, it provides us a very convenient way to derive the vector components of our normal projection directly from the vector components of the vector itself. Okay, well now let's look at a couple of identities that relate to this operator. First of all, this one, Pii. We're going to contract I and j here, and we'll just use our definition right here to see what that looks like. That's ni contracted with ni in the lower position. Well, surely you recognize this as just the dot product of our normal vector, and of course that's equal to 1. We have a unit vector, so the contraction of I with j here just produces a value of 1. Okay, another identity that shows up and is quite useful and important is this one, Pik contracted with Pkj, like this. Okay, we'll use our definitions here. Pik is just Ni times Nk. So that's the equivalent of Pik. And then we'll use the definition again for this one. That's going to be Nk contracted, or just multiplied by Nj. j like this. Okay, well, surely you see it. These two terms right here, the same as this. It's just a contraction of the vector components of our normal vector right here. And that's equal to 1. So these two terms in the middle just collapse out and leave us only with the first and third terms here. So in the end, this is equal just to ni in j, which according to the definition up here is nothing more than our original operator pij. Alright, so the import of this is that when we combine these two this way, when we contract them like this, then it acts a lot like the delta factor. If we had delta ik times delta kj, we're going to get delta ij. This index is in effect absorbed, and the result over here has the indexes that are the same here and here. And what that tells us in geometric terms is if we apply our new normal projection operator to itself, we just get the normal operator again. So it's a repetitive operation that we could do it a third time and we'd still get just 1. So every time we apply the operator to itself, it collapses into a single operation. All right, so I think that pretty much describes the normal projection operator. So let's move on to another object that's very similar, relating to our surface projection. This time we have these two expressions that we also ran into in the last video, only this time they involve the components of our surface projection, Ti. Alright, so what do we have? We've got Ti, the vector components of our surface projection in ambient form, as a function of T alpha, which are the vector components on the surface. Well, what we're going to do is the same thing we did before. We're going to use this second expression here to eliminate T alpha. And the second expression, of course, is T alpha as a function of our vector components Vi. So it's going to look like this. We're going to have Ti is equal to this first term, our shift tensor Zi alpha, and then times T alpha, but in this form over here. So it's going to be Z alpha, and of course I cannot use I because it's already being used as a free index. So I have to use a different letter here. We'll use J. All right, so with this then, we now are able to define the second new object, and that's going to be the surface projection operator. And as before, we can now rewrite the expression here. Ti is simply our new operator, Tij, contracted with the vector component Vj. So I'm sure you can see the parallel here. This looks very similar to what we just did for the normal projection operator. And again, same concept. We have an operator here that operates on our vector components Vj, this time to give us the vector components of our surface projection instead of the normal projection. All right, let's look at the object here. Same kind of comments as before. It's a second rank tensor. We know it's a tensor because each of these are tensors. When we combine them together, we'll get a tensor. Being second rank with the ambient indexes, it's going to be 3 rows, 3 columns. It'll be a square matrix. Well, what about the symmetry of it? What if we lower I, raise J? We can lower I here, raise J here. We can flip the position of our dummy index. Remember, we can always do that. We can raise one and lower the other. When we do, we flip the order of these terms. We get the exact same expression if we raise and lower all these indexes accordingly. So that again means that this second rank tensor is symmetric with respect to I and J. Okay, now the normal projection operator was just the product of the vector components. It's a vector product of Ni with Nj, just a simple vector product. Here we have a contraction. Now, back in one of the earlier videos where we were introducing the idea of the shift tensor, you'll remember if we had a contraction in this direction along the ambient indexes, we were going to get a delta function with this index and this one. Now, at the time, you'll remember that we made the point that that only works if we're contracting the ambient index. What we said at the time, if we contract the surface indexes, we're not going to get a delta function. We said that was going to have a totally different meaning. Well, this is that totally different meaning. Here we have a contraction along the surface indexes like this. It does not produce a delta ij factor, it produces an operator, the surface projection operator. And that is the alternate meaning of the contraction of the indexes for these two objects right here. Okay, well, what about the identities here? Do the identities work in a similar fashion? Well, let's find out. Let's start with TII. And of course, we'll just use our definition. That's Zi alpha contracted with Z alpha I this time. And now what we do have is a contraction along the ambient index, which means that the result is going to be a delta factor with these indexes. In other words, this is just equal to delta alpha alpha. And of course, in a two-dimensional surface where alpha can be 1 or 2, then this expression just resolves to the value of 2. So whereas the contraction of Pii was equal to 1, Tii is equal to 2. Now, I leave it in this form because if we happen to be working with a hypersurface where the values of alpha can be 1, 2, or 3, for example, then delta alpha alpha would be equal to 3. So this value over here is equal to the dimensionality of the surface we're working with. For normal surfaces, of course, that's just a value of 2. All right, what about the other identity, Tik times Tkj? What if we have this contraction? What happens there? Well, use our definition. First term is Zi alpha times Z alpha k. These two factors are Tik. Use the definition again for Tkj. It would be Zk. Can't use alpha. I've got to use beta. And then times Z beta j. So these last two factors equate to Tkj. All right, surely you see it right here. There is a contraction on the ambient index, which means this expression is really delta alpha beta. And then I could write it out in separate terms, but by now you've seen this sort of thing often enough. I think we can do it in one step. You'll see that this index is absorbed here, leaving just alpha. So that means that the result of this expression is just going to have the two terms in it, Zi alpha, and this last term, which is becoming Z alpha j because the beta index was absorbed. Well, of course, this is just our definition for Tij. So this is all equal to Tij, and the result is that the effect is exactly the same as we saw with the normal projection operator. And that is, if we contract these two along this index here, then the k index is absorbed, and I and j become the indexes of our operator over here. So again, if we apply this operator to itself, we're going to get the operator in return. Now, this behavior might make more sense if we think about it in geometric terms. Think about this. If you apply the operator up here to a general vector, you're going to get a projection on the surface like so. Well, if we apply the operation again to this result, then we're applying a surface projection operator to a vector that's already lies on the surface. So it makes sense that the surface projection of a vector that already lies on the surface is the vector itself. So it doesn't make any difference how many times you apply this operator again, it's only the first operation that results in this projection. After that, additional applications of this operator will just produce identical results over and over again. And the same is true for our normal projection operator. So maybe that'll help to explain what this particular identity is all about. Okay, so now you've seen the normal projection operator and the surface projection operator. Well, do these things have any practical value? Well, the answer to that is yes. We're all familiar with computer programs, for example, that are used in gaming software or maybe computer-assisted design programs, CAD applications, that involve examining three-dimensional objects and displaying the results in two dimensions. You know, you can only see it on a computer screen that's flat, a two-dimensional screen, but we're dealing with three-dimensional objects. Well, if we have those objects represented in a computer program, they would be vectors like this that represent each of the points in three-dimensional space of whatever object we're talking about. But to display them where you can see them on a flat screen, we have to project the results onto a flat screen. So this kind of operator is extremely useful in computer programs that allow you to rotate and move and translate these three-dimensional objects, and that's what gives them such a realistic view when they're applied in that fashion, again in gaming programs or in CAD programs. Okay, so that's pretty much it for the normal and the surface projection operators, except I've got one more identity I want to show you that involves a combination of the two together. So let's go look at that. This time we'll start with the basic relationship that our vector component VI is just going to be the sum of the vector components for the surface projection and the normal projection. Okay, now we're going to substitute into this expression the values that we've just been working with involving our operators. So TI is going to be TIJ contracted with VJ, and PI is going to be PIJ contracted with VJ again. So these two expressions are the equivalent of TI and PI. But on the left-hand side, what I want to do is to express VI as the contraction of VJ with delta IJ. Now, remember how this works. If we saw this expression to begin with, we'd know that we can absorb the J index, and this product would then resolve to this. So these two expressions are absolutely equivalent to one another. All right, but what we have then is the fact that there's a common factor, Vj, that we can eliminate from all the terms throughout the expression. And that leaves us with the identity I wanted to show you, and that is that delta ij here is going to be the result if we just add the two operators together. And I'll write them in the opposite order. That's the way we normally see it. So pij plus tij will result in delta ij. And for completeness, I'll just expand them out over here. So Pij is just Ni times Nj, you remember, and Tij is the contraction of our shift tensor I alpha with the inverse of our shift tensor alpha j. So this is the identity that I wanted to show you. Okay, now as we wind down, let me suggest a couple of things we can do here. First of all, what happens if we form a contraction here? What if we make this I, and this I, and this I? What happens? Well, delta II, they're ambient coordinates. The indexes could be values of 1, 2, or 3, so delta II is a value of 3. Well, we just said that PII is a value of 1, and TII is a value of 2. So it makes perfect sense. 3 is certainly equal to 1 plus 2. So that shows you that this is consistent with this new identity. Okay, and finally let me recommend some activity offline for you. This will be really good practice for you in working with all of these objects and solidifying your understanding of everything we've been working with in the last few videos. Start with this expression, Ni, Nj, and expand it out using the explicit definition for these components. You remember we have the definition for ni in the upper position and lower position involving our Levi-Civita symbols and so on. So express those that way and simplify what you get on the right-hand side, and you will be able, if you do it correctly, to ultimately derive this expression right here. You'll be able to prove this identity just by simplifying the explicit definitions of this product right here. Now, to do that, you're going to need to understand the definitions of these components. You're going to need to work with the delta functions, as we've done several times before, and you're going to need the identities that involve the shift tensor and the identities we've developed concerning our operators. But if you combine all that together, then you'll be able to prove that this expression is equal to delta ij minus this expression, which of course is the equivalent of this identity. Okay, with that, we'll wind the video down and go do a quick recap. What we did in this video was to define two new objects called operators. We defined the normal projection operator this way and the surface projection operator this way. Now both of these operators function the same way. They are operators that we apply to our vector components Vj like this, and the results that they give are, first of all, for the normal projection operator, we'll get the vector components of the normal projection here. And in this one, we'll get the vector components of the surface projection like this. So these operators give us a very convenient way to take the vector components of any vector v and find the normal and the surface vector components, just like this. Okay, the next thing we did was to derive a number of identities for these operators. We said that the contraction of the indexes for our normal projection operator just gives us a value of 1, but the same operation of contracting the indexes for our surface projection operator gives us a value of delta alpha alpha. For normal surfaces, that's just 2, but we emphasize the fact that if we're working with hypersurfaces, then the value is going to be equal to whatever the dimensionality is for the surface. Okay, and then both of these operators exhibit this behavior. If we contract them with themselves, if we apply the operator to itself, then it's just going to result in the operator again. It absorbs this k index here, this dummy index, in the same way that would happen if these were delta factors. Delta ik kj would give us delta ij. So these work the same way. And finally, the sum of the two operators added together give us the delta function like this. Okay, in the next video, we're going to use these results to demonstrate what these operators look like for each of our sample surfaces.